So what is a matrix? A matrix consists of rows and columns. Similar to a table, ladies and gentlemen, that's what a matrix is. All right. This is an example of a 2x2 matrix. Now, when we say 2x2, that's to say that this matrix has 2 rows by 2 columns. So an example of a 2x2 matrix would be this here. That's a 2x2 matrix. It has 2 rows and 2 columns. Okay. If I call this matrix A, we would say that the 1-1 entry, the 1-1 entry of the matrix is the row 1, column 1 entry. And the 1-1 entry of this matrix denoted as A sub 1-1, 1-1 entry. The row 1, column 1 entry of this table is going to be 1. The 1-2 entry of this matrix is the row 1, column 2 entry. Denoted symbolically like this, the 1-2 entry. And the 1-2 entry of this table is the row 1, column 2 entry, which is 3. The 2-1 entry is the row 2, column 1 entry. And what do you think that is? What is the 2-1 entry for this matrix? Anybody want to guess?
A21 equals.
What is the row 2, column 1 entry in this matrix? You're on the right track.
5.
5, right there. 5 is the row 2, column 1 entry. That's the 2-1 entry. What's the 2-2 entry of this matrix? That's the row 2, column 2 entry. Denoted symbolically as the 2-2 entry, and that would be 7. 7 is the row 2, column 2 entry. You see that there? Any questions about that 2x2 matrix, ladies and gentlemen? All right, when the number of rows is equal to the number of columns in a matrix, we call the matrix a square matrix. So this is an example of a square matrix. A square matrix, again, occurs when the number of rows is equal to the number of columns. Notice 2 times 2 is 4. That means this 2x2 matrix has 4 entries. The 1-1 entry, the 1-2 entry, the 2-1 entry, the 2-2 entry. Okay. Any questions about that? What would be the diagonal, the main diagonal entries of this matrix? The main diagonal entries. The main diagonal entries of this matrix would be the 1-1 element, which is 1, and the 2-2 entry, which is 7. We call this, ladies and gentlemen, the main diagonal of the matrix. The main diagonal. Everybody see that there? Main diagonal. The 1-1 entry is 1. The 2-2 entry is 7. 1 and 7 are on the main diagonal of this 2x2 matrix. Any questions about this so far? 5 we say is below the main diagonal. 3 we say is above the main diagonal. All right. Okay. What if matrix B is a 3x2 matrix? That means matrix B has how many rows and how many columns?
2 row. Oh, wait, 3 rows, 2 columns.
3 rows by 2 columns. Called a 3x2 matrix. This would be the 1-1 entry, the 1-2 entry, the 2-1 entry, the 2-2 entry, the row 3 column 1 entry, the row 3 column 2 entry. A 3x2 matrix, 3 rows by 2 columns. Does that make sense? 3x2. Ladies and gentlemen, there is no main diagonal for a non-square matrix. This is a non-square matrix. Why is it non-square?
It's not a perfect square.
Well, it's not a perfect square in the sense that the number of rows does not equal to what? The number of columns. Do you agree? It does not have the same number of rows as columns. Think of it that way. So it's a non-square matrix. So only square matrices have a main diagonal. This does not have a main diagonal. All right. Any questions about these so far here? How many entries does a 3x2 matrix have? What's 3 times 2?
6.
Should have 6 entries. 1, 2, 3, 4, 5, 6, correct? Oh, by the way, these should not be A's. They should be what?
B.
Yeah, they should be B's because I call this matrix B. Matrices are usually, the names of matrices are usually denoted in uppercase letters. The entries are usually denoted in lowercase letters, okay? All right. All right, so matrices, ladies and gentlemen. Matrices are going to enable us to solve systems of 2 and systems of 3 linear equations and 2 or 3 unknowns. All right. But before we can do that, we have to, first of all, cast our systems of linear equations in the form of a matrix. So let's go to our textbook. This is section 6.1 in our textbook. Okay, hold on a second here. All right. This is section 6.1 we are covering today. I would again strongly recommend, ladies and gentlemen, that you look at the examples in this section. By doing that, you will gain a deeper understanding as to what's really going on in this section. Okay, so please do take the time to look over, these examples. If nothing else, look over the examples that your author works through in these sections. Invaluable information here. Look at all the work, look at all the steps your author is showing in this example. That would take me about an hour to write all those steps out. Well, not an hour. It would take me a while. So please do invest in your textbook a little bit by looking at the examples. It's all laid out there. It'd be a shame if you did not invest in your textbook. You paid money for it. Just try to put it to use. Okay. All right. Page 572. I wanted to look at problem number 9. What they want us to do, ladies and gentlemen, is first of all, they want us to learn how to write a system of linear equations in the form of a matrix, specifically called an augmented matrix. Okay. And we're never going to be able to solve these systems using matrices until we first of all learn how to do that. So problem number 9 on page 572 in your textbook. And if you're taking notes, which I hope you are, I would definitely just write down problem 9, page 572, and then follow along, okay? All right, always indicate the page numbers that I read out, that I indicate during the session here. So what we're going to do is we're going to take this system of 3 linear equations and 3 unknowns, and we are going to write this system in the form of a matrix. So first of all, I'm writing the system down on my paper before I go to my my DocCam. 1. Okay, so we're going to take this system of 3 linear equations and 3 unknowns, and we're going to now write it as a matrix. Okay. Specifically, ladies and gentlemen, there's going to be how many rows to this matrix? There's going to be how many equations we got?
3.
So there's going to be 3 rows. This will be row 1 of our matrix, row 2, and row 3. There's 3 rows. By how many columns? There's 4 columns, 4 columns. Okay. We'll call this column number 1, column 1, column 2, column 3, and column number 4. Notice we have like terms lined up in columns, the X terms, the Y terms, Z terms, constant terms. So we're going to write this as a 3x4 augmented matrix. This system. Now, when we cast this system in the form of a 3x4 augmented matrix, ladies and gentlemen, we're not going to see any variables in our matrix. We're just going to see numbers. That's all we see. So row 1, we put the coefficients of our equation and including the right-hand side. So we're going to put -3, 2, -1. Then we're going to have like a vertical little dash line. Some books have a vertical dash line. Some have a solid vertical line. Doesn't matter. And then on the right side of this dashed line or solid line, we're going to put the constants of our equations. Ladies and gentlemen, I have just entered in the first equation into my matrix in the row 1. Notice how my first equation looks in matrix form in row 1. You don't see any variables. All you see are the coefficients. That's it, and the constant. Row 2 is going to go in, equation 2 is going to go in for row 2 of this matrix. We have 8. Now, I don't have any Y variable here, so what am I going to put in place of it? What am I going to put in place of my missing Y variable in the second equation? I'm going to put 0. Coefficient of Z is 4. The right-hand side constant for equation 2 is 12. That's your second equation entered into your 3x4 augmented matrix. The third equation is going to constitute the third row of my matrix. I don't have any X term for my third equation, so it's understood to be 0x. So I put 0 in for its coefficient. 2, -5, 1. Ladies and gentlemen, you are looking at the answer to problem number 9 on page 572. All they wanted you to do is they just wanted you to take this system of 3 linear equations and 3 unknowns and just rewrite it in the form of a augmented matrix. We have done that. Pretty simple, isn't it? That's all we want to do so far. Just write a system as a matrix, equivalent matrix. All right. So we're done with that problem. That's number 9. All right, that's number 9. See if we can do maybe another one there. Any questions about that one? All right, problem number 11. Let's see if we can write this system of 2 linear equations in 2 unknowns in matrix form. But, ladies and gentlemen, we spot that we have a situation here. What is it? What do you notice about this equation? This system. What do you notice about the system?
There's variables on the right side of an equation.
Yeah, it's all messed up. It's all out of whack. We want to have our systems where all our equations are in per se standard form, ladies and gentlemen, where we have all of our X's lined up, Y's, Z's lined up on the left side of our equations, and the constants lined up on the right side. We don't have that with this system. We have to, first of all, fix this system. So we have to do a little algebra, first of all, here. We're going to have to distribute the 4. So we'll have 4x minus 8y equal to 6y plus 2. I'm going to drag the 6y over to the left side by subtracting 6y from both sides. In which case, after doing that, my equation now will be 4x minus 14y equals 2. Now we fix that first equation. Now it's in standard form. Let's do the same thing with the second equation. To get this in the standard form, we have to move the 5y over to the left to join the x. To do that, we subtract 5y from both sides of our equation. And when we subtract 5y from both sides, now our second equation is going to be in the proper form of 3x minus 5y equal to 7. Ladies and gentlemen, we now have our system of two linear equations and two unknowns in the proper form. Okay. Now it will be very easy to portray this system of two linear equations and two unknowns as a augmented 2 by what? 2 rows by how many columns? 2 rows by
3.
3 columns. So now we're going to write the system as a 2 by 3 augmented matrix. And here we go. So the first row is going to be the coefficients and the constants, the constant of our first equation. So this is going to be 4, negative 14, 2. We would have our vertical dashed line that separates the left-hand side coefficients from the right-hand side constants. Second equation slides in for row number 2. The 2-1 entry would be a 3. The 2-2 entry would be a negative 5. And the 2-3 entry would be 7. We are done. Ladies and gentlemen, this would be your 2 by 3 augmented matrix that represents this system of two linear equations and two unknowns. Questions how we're rewriting systems of linear equations as augmented matrices. That's all we're doing so far. Okay. Any questions about anything on this page so far? Number 13, let's try to do the same thing. Let's try to write this system of equations as an augmented matrix. Number 13. Well, what do we notice? We notice that the first equation is x equals 2. The second equation is y equals 2. The third equation is z equal to negative 1/2. They want us to write this system of 3 linear equations and 3 unknowns in augmented matrix form. Now, how many equations do we got? We got 3, so we're going to have a 3 by what? How many columns? 1, 2, 3, 4 columns. Do you agree? A column for the x variables, a column for the y, column for the z, and a column for the right-hand side constants. So this is going to be a 3 by 4 augmented matrix. All right, here it goes. The first equation will be the first row, which means we just have 1. We don't have any y or z terms, so we got 0, 0, 0 for the y, 0 for the z, and we got 2 for the right-hand side constant. Second equation, we don't have any x term in the second equation, so we have 0 for the x, missing x terms coefficient. We have 1 for the y coefficient, and we have 0 for the z coefficient. There is no z term in the second equation. And then we got 2. Finally, the third row is going to be our third equation. And notice in the third equation, we don't have any x or y. And because of that, we're going to have to put in what? Zeros for the coefficient of x and y, and z's coefficient would be 1. And the right-hand side is going to be negative 1/2. This is going to be 0, and that'll be 0. Ladies and gentlemen, do we understand how we entered this system of 3 linear equations and 3 unknowns in the form of a 3 by 4 augmented matrix? Notice for this system, we have 1s on the main diagonal. 1s are on the main diagonal. The 1-1 entry is a 1. The 2-2 entry is a 1. The 3-3 entry is a 1. All the other entries below the main diagonal and above the main diagonal are zeros. Notice that. Okay. All right. So if I give you a system of linear equations, you should be able to rewrite it in the form of an augmented matrix. Does that make sense? You think we can do that at least? That should be pretty simple, right? To do that. Well, let's see. So ladies and gentlemen, for classwork number 1, see if you can do problem number 10 here. Just write that as an augmented matrix. This problem should take about no more than about 1 minute. Number 10, write it as an augmented matrix, that system. Classwork 1, problem 10. Today is November 17th. All we're doing is writing that system of 3 linear equations and 3 unknowns in the form of an augmented matrix. That's all we're doing. So it should be pretty simple. All right, let's check our answer. Did you guys get that? Problem number 10. That's just a what by what augmented matrix. How many rows?
3 by 4.
3 rows by 4 columns, augmented matrix. That's that system cast in the form of a 3 by 4 matrix. Pretty simple so far?
Yeah.
All right. Let's try to go backwards, ladies and gentlemen. Suppose we're given an augmented matrix and we're being asked to recover the original system of equations that it represents. We should be able to go backwards. So suppose that, and I believe this is number 16 in your textbook. Suppose that we're given this augmented matrix here. You know what? I think your author's using a solid vertical line. It don't matter if it's a solid or dashed vertical line. It just separates your left-hand side coefficients from your right-hand side constants. It don't matter. Some books have a vertical dash line, some have a solid. There's no difference. All right, so how many rows does this matrix have?
2.
So this is a 2 by what? 2 by 3 augmented matrix. And I claim that by looking at this matrix, we should be able to recover the equations in this system. Ladies and gentlemen, your first column represents the coefficients of the x variables in the equation. The second column represents the coefficients of the y variable in the equations. The rightmost column represents the right-hand side constants of the equations. So from our first row, we should be able to recover what equation? Negative 3x plus 7y equals, this vertical line means equals negative 2. There's your first equation in your system. The second row yields what equation? Negative 1x plus 1y equals 4. Done. That's your answer. Pretty simple, isn't it, going backwards?
Yes.
Okay. So let's see if we can do number 17 now. Given this 3 by 4 augmented matrix, we should be able to derive the system of equations that it represents. Remember, the first column represents the coefficients of the x variable, second column represents coefficients of the y variable, the third column represents the coefficients of the z variable, and the right-hand side column represents the constants of the equation. So the first row yields what equation?
1x plus 4y plus 3z equals 8.
That's all there is to this, ladies and gentlemen. No, that should be 3z equals 8. That's all there is to this. Second row represents what equation?
Y plus 2z equals 12.
That's right. We don't have any x in the second equation. Notice it's technically 0x, but 0x means we just omit x. Third row does not have an x, does not have a y, it just has a z. So this would just be z is equal to what? 6?
Yeah.
There's your system, ladies and gentlemen, from that 3x4 augmented matrix. It's pretty easy going back and forth between system to matrix, matrix back to system. All right, we're good on that so far? All right, so you guys do this one. This is classwork number 2. This should take you, like I said, no more than 1 minute for this problem. I want you to rewrite this 3x4 augmented matrix in the form of a system of equations. All right, go to it, ladies and gentlemen. What system of equations would this matrix represent? Classwork 2. This problem should not even take more than 30 seconds, actually. Shouldn't even take much more than 15 seconds. What's the first equation?
X equals 2.
X equals 2. What's the second equation?
Y equals 6.
Y equals 6. Third equation.
Z equals negative
There
5.
you go. That's it. Am I getting this here? Pretty simple. All right, that's classwork 2. All right, now page 565 in your textbook. Write that page number down in your notes. Page 565. 565. Wait a minute. 565. Wait. 565. All right, ladies and gentlemen, make a note in your notes that we're looking at the top of page 565 in our textbook, so that later on you can maybe go back and revisit and trace your footsteps along this lecture here. Page 565. Ladies and gentlemen, in order to solve systems of linear equations using matrices, we're going to have to utilize what are called elementary row operations. There are 3 legal elementary row operations that we can use to solve systems of linear equations using matrices. So we're going to look at these 3 legal elementary row operations that we have at our disposal. The first elementary row operation that we can always use in a matrix, ladies and gentlemen, is we can always interchange any 2 equations, which means we can always interchange any 2 rows of a matrix. Always. Perfectly legal to do. Because stop and think about it. Do you agree this system negative 3x minus 5y equals negative 13 and the second equation x plus 2y equals 5 is the same as the system if I just flip-flopped equations? Do you agree it's still the same system?
Yes.
This is an obvious, reason why this is a legal elementary row operation. You can always interchange any 2 rows of a matrix, because interchanging the rows just means you interchange the equations. You just put one equation on top of the other one. No big deal. It's still the same system. Still has the same solution. All right, another legal elementary row operation that we have at our disposal is we can always take an equation and multiply both sides of the equation by some constant. Did we not utilize that technique to solve systems using the elimination method in the past? You remember that? In other words, to solve this system here, x plus 2y equals 5, negative 3x minus 5y equals negative 13. If you wanted to eliminate the x variable, would you not multiply the first equation, both sides, by 3? Isn't that true?
Yeah.
So, ladies and gentlemen, another valid, legal, elementary row operation is you can always multiply any row of a matrix by any non-zero constant. That's equivalent to as if you just multiplied both sides of an equation by that constant. One last valid elementary row operation that we can use is we can always take an equation, multiply it by a non-zero constant, and then add it to another equation to produce another equation. In other words, if you look at this system, x plus 2y equals 5, negative 3x minus 5y equals negative 13. Do you agree that to eliminate the x variable, first of all, I would multiply the first equation by 3? Then I would add that equation to the second equation to produce this third equation that says y equals 2. Do you agree? And so, as I'm on the third valid elementary row operation says that I can always add a multiple of one row to another row of my matrix. So here you go. Here's these 3 elementary row operations cast in the form of matrices. So in other words, the first example up here, ladies and gentlemen, is cast in the form of a 2 by 3 augmented matrix. Do you agree? They put this system negative 3x minus 5y equals negative 13. X plus 2y equals 5 in the form of a 2 by 3 matrix. And by interchanging these 2 equations, that's equivalent to as if I just interchanged the 2 rows of these matrices. Do we understand? By interchanging rows 1 and 2, that's equivalent to as if I just interchanged rows equations 1 and 2, just flipped them upside down. It's still the same system. Do you agree? Still the same system. It'll still have the same solution. And that's why it's valid to always interchange any 2 rows of a matrix. The second example has us multiplying equation 1 both sides by 3. That's illustrating that I can always take any row of a matrix and multiply it by a non-zero constant. If I multiply the first row of this 2 by 3 matrix by 3, I generate the equivalent 2 by 3 augmented matrix to the right. That's equivalent to as if I really multiplied the first equation both sides by 3 and generated an equivalent equation. The third elementary row operation says, ladies and gentlemen, what I could do is I could add to row 2 a multiple of row 1. In other words, I could take row 1 multiplied by 3 and then add those results to row 2 to form a new row 2. Let's look down here. If you take 3 times row 1, you get 3, 6, and on the right side you get 15. If you then add those entries to row 2, whose entries are negative 3, negative 5, negative 13, you produce a brand new row 2, whose entries would be 0, 1, and 2. Is everybody following this third elementary row operation at the bottom here? What's going on? Anybody confused about the third elementary row operation? What happened? You can always add a multiple of one row of a matrix to another row to produce another equivalent row. Okay. So here again, they added 3 times the first row to the second row to produce a new equivalent row 2. Any questions about these valid 3 elementary row operations, ladies and gentlemen, that we can use in matrices, which are analogous to really using them with systems of equations up here? All right, it's these elementary row operations that are going to ultimately enable us to solve systems using matrices. Okay. All right, page 572. Let's go to page 572. Make sure you write that down in your notes. Page 572. We're now going to look at examples 21 through 32. Page 572, examples 21 through 32. Let's go down and look at some of these. All right. In these examples, they give us a matrix. Notice for problems 21 through 26, they give us this 2 by 3 augmented matrix. And then they're going to have us, ladies and gentlemen, perform some elementary row operations on this matrix to produce an equivalent matrix. So let's see if we can do a couple of these problems. So we will try to do problem 21 first. So I'm going to write down this 2 by 3 matrix first on my paper. Okay. Now, in problem number 21, what do they want us to do, ladies and gentlemen? What is this notation saying to do? What do you think? What's that notation saying to do in problem 1? What elementary row operation are we going to subject this matrix to?
To flip them.
We're gonna flip what?
The bottom of the matrix with the top.
We're just gonna interchange rows what? 1 and 2, do you agree? That's all we're doing. That is a valid elementary row operation. You can always interchange any 2 rows of a matrix because technically that means in a system of equations, you're just interchanging the equations. Equation 2 becomes equation 3, equation 3 becomes equation 2. It's still the same system, still equivalent. So I could put the equal sign here and say that this 2 by 3 matrix is now going to be equal to this one after I interchange rows 1 and 2. And we're done. We have just flip-flopped rows 1 and 2. Do you agree? And these matrices are still equivalent to each other. Do we understand that they're still equal to each other? Still the same system of systems of 2 equations and 2 unknowns? Isn't that true? Still the same system of 2 equations and 2 unknowns. All right, that was problem number 21. Let's look at another problem. Problem 22. Let's see. Problem 22, ladies and gentlemen, what do they want us to do here? They want us to take row 2 and multiply it by what constant?
Negative 1/3.
Negative 1/3 to form a new row 2. So what we're going to do in problem 22 is we're going to take row 2, multiply it by negative 1/3 to form a new row 2. I like to call this a new row 2. Okay. All right, let's show that down here. So we're going to take negative 1/3 and multiply it by the row 2 entries. The row 2 entries are going to be negative 3, 6, and 6. And then we're going to form a brand new what row 2 after having done this. So what's negative 1/3 times negative 3? Positive 1. What's negative 1/3 times 6? Negative 2. What's negative 1/3 times 6? Negative 2. So therefore, ladies and gentlemen, after having performed this elementary row operation, my 2 by 3 augmented matrix here is going to become what equivalent 2 by 3 augmented matrix? Notice row 1 did not change. We did not do anything to row 1. It was row 2 that we transformed. There you go. I still claim that these matrices are equivalent to each other because these systems of 2 equations and 2 unknowns are still equivalent to each other. The effect that we had on equation 2 of the system is we really multiplied both sides of equation 2 by negative 1/3. That's why we still have an equivalent equation number 2. This equation is still equal to this equation. Hence, these matrices are still equivalent. Now we understand that elementary row operation. You can always multiply any row by a matrix by a non-zero constant to generate a new equivalent row. That's a valid elementary row operation. All right, any questions about that one? All right. Now let's jump down to number 26. What's happening in problem 26, ladies and gentlemen? What are we doing in problem 26?
You're timesing the first row by 3 and then adding the second row to it to make the new second row.
That's right. So what we're doing is we're taking a multiple of row 1, adding it to row 2 to form a new row 2. That's a valid elementary row operation. You can always add to a row a multiple of some other row in a matrix to form a new row. All right, so that's what we're going to do here. So, and this would be a new row 2. I like to put the word new, so it's like a reminder it's the new row 2. So here's what we're going to do here. I'm going to take, first of all, 3 times row 1. Row 1 is 1, 4, and the right-hand side is 2. And then to that, I'm going to add row what? Row 2. Well, let's do that. What's 3 times 1? 3. What's 3 times 4? 12. What's 3 times 2?
6.
And to that, we're now going to add what? Row 2. To form a new row 2. So, ladies and gentlemen, this would be my new row 2 here at the bottom. My new row 2 is going to be 3 plus a negative 3, which is going to be 0. 12 plus 6 is 18. And 6 plus 6 is 12. New row 2. Therefore, I claim that this matrix is going to be equivalent to this matrix. Notice we did not change row 1. We used row 1 to change row 2. We did not change row 1. Row 2 underwent a change. Ladies and gentlemen, this matrix is still equivalent to this matrix. Everybody understand that elementary row operation that just occurred there? We took row 2, we added 3 times row 1 to it to form a new row 2. You may see this? Do we understand these 3 elementary row operations? You can always interchange any 2 rows. You can always multiply any row by a non-zero constant. You can always add a multiple of 1 row to another row of a matrix. These are 3 valid elementary row operations that are going to enable us to solve a system of equations using matrices. Okay. All right. Well, if you understand those, then, ladies and gentlemen, let's see if we can back up here. Classwork number 3, ladies and gentlemen, I want you to do problem number 25. I want you to take 1/3 times row 2, add it to row 1 to form a new row 1. Go ahead and do that. Classwork number 3, 25. Did you get that? Anybody get that correct? Are we getting this, ladies and gentlemen?
Yeah, I got that.
You see how we formed a new row 1 by multiplying row 2 by 1/3 and then adding it to row 1? That's a legal elementary row operation. You can always add a multiple of 1 row of a matrix to another row to form a new row. You can always do that. Notice we did not change row 2. We did not change row 2. We used row 2 to change row 1 into an equivalent row 1. That's what we did. All right, these are 3 valid elementary row operations that we can utilize now to begin to solve systems of equations using matrices. And so how are we actually going to solve systems now, ladies and gentlemen, using matrices? Well, first of all, do we all have this? Are we good on this classwork 3 here? Everybody have this accounted for one way or another? All right, I'm going to get rid of this, ladies and gentlemen. Classwork 3. All right, hold on a second here. Okay. Let's go to our textbook. We're gonna go to page 566 in our textbook. Write that down in your notes, page 566 now. 566. Hold on a second here. There's 566 here. Okay. All right, ladies and gentlemen, on page 566, there's a definition in the purple box, page 566. Row echelon form and reduced row echelon form. What do these things mean? Well, on page 566 in the purple shaded box here, what is the definition of a matrix that is in row echelon form? We say that a matrix is in row echelon form if it satisfies the following requirements. Number one, any row in a matrix that consists entirely of zeros must be at the bottom of the matrix. Number two requirement, for all other rows, the first non-zero entry is 1. So for all the other rows, ladies and gentlemen, as you move from left to right in a row, the first non-zero entry you run into must be a 1. We call this the leading 1. Number 3 requirement, the leading 1 in each non-zero row is to the right of the leading 1 in the row immediately above it. What does that mean? That's about as clear as mud, that third requirement there. We'll show you with examples. So let's look at these down here. Here are some examples of matrices that are in row echelon form. Page 567, examples of matrices that are in row echelon form. You see this matrix, this 2 by 3, 1, 5, 3, 0, 1, 6. We say that's in row echelon form. Why? Well, do you agree that we don't have any we don't have any rows that consist of all zeros? If we did, they would have to be at the bottom of the matrix. We don't have that situation here. The second requirement is, as you move through a row from left to right, the first non-zero entry you have to run into is always a 1. Do you agree the first non-zero entry I run into in row 1 from left to right is a 1? You agree that the first non-zero entry I run into in row 2 from left to right is a 1? That requirement is satisfied. The third requirement says this. The leading 1 in row 2, ladies and gentlemen, has to be in a column that's to the right of the column that contains the leading 1 of the first row. Let me say that again. The leading 1 that occurs in row 2 must be in a column that is to the right of the column that contains the leading 1 in row 1. Is that the case? That is the case. For that reason, we say this matrix is in row echelon form. Here's another example of a matrix that's in row echelon form. This is a 3 by 4 augmented matrix. Notice we don't have any row that consists entirely of zeros. If we did, it would have to appear at the bottom of the matrix. Number 2 requirement. Notice the first non-zero entry you run into in any row is a 1 from left to right. We do so in the first row. The first non-zero entry we run into in row 2 from left to right is a 1. The first non-zero entry we run into in row 3 from left to right is a 1. Do you agree? That requirement is satisfied. Third requirement. The leading 1s that occur in subsequent rows have to be in columns that are further to the right than the columns that contain the leading 1s in the previous row. In other words, ladies and gentlemen, notice the leading 1 of row 2 is in column 2. That's in a column that's to the right of column 1 that contains the leading 1 of row 1. The column that contains the leading 1 in row 3 is in column 3. That column is to the right of column 2 that contains the leading 1 in row 2, which is to the right of the column that contains the leading 1 in row 1. Is this making sense so far? What it means for a matrix to be in row echelon form. Making sense, ladies and gentlemen, so far? Notice this third matrix over here is in row echelon form. Notice this matrix does have a row consisting entirely of zeros. If that's the case, that row must occur what? At the bottom of the matrix. Requirement number 1. Notice that. Well, it is at the bottom of the matrix. Requirement number 2, for all other rows, the first non-zero entry must be a 1. This is called the leading 1. You agree, as we move from left to right in any row, the first non-zero entry we hit is always a 1. Unless we go to the bottom row where it's all zeros. That's an exception. Notice requirement 3 requires that the leading 1 in each non-zero row is to the right of the leading 1 in the row immediately above. In other words, the leading 1 of row 2 is in a column that's to the right of the column that contains the leading 1 of row 1. This is said to be in row echelon form. Any questions so far about row echelon form? All right, ladies and gentlemen, why is this matrix not in row echelon form? Why is this matrix not in row echelon form? Hold on, I'm not done yet. Why is this not row echelon form?
The row with all zeros isn't at the bottom.
That's right. This row of all zeros has to be at the bottom. That was one of the requirements. Everything else is satisfied though. Notice the first non-zero entry you run into moving from left to right in any row is a 1. And notice the 1 in row 3 is in a column that's to the right of the column that contains the 1 in row 2. Everything else is satisfied, but because we have zeros, this row of zeros not appearing in the bottom of our matrix, this is not row echelon form. Not row echelon form. How about this matrix? Why is this matrix not in row echelon form? Ladies and gentlemen, why is this matrix not in row echelon form? Well, we don't have a row consisting entirely of zeros. We don't have that. We don't have that issue with this one. The first non-zero entry we run into from left to right in each row is a 1. No issue with that. What's the issue?
The second one isn't to the right of the first one.
Exactly. Notice the leading 1 of row 2 is not in a column that's to the right of the column that contains the leading entry of 1 in the first row. You see that? This is not row echelon form because this one would have to be at least in column 2 or 3 over here. It would at least. In fact, it would have to be only in column 2. It could not be in column 3 because then these ones would be in the same column. That's not row echelon form. All right. So maybe one more here. Why is this matrix not in row echelon form? Why is that not row echelon form, ladies and gentlemen? The first non-zero entry we run into from left to right in any row is a 1. That's okay, but what's the problem here? Why is this not row echelon form?
They're not ordered correctly.
As far as the columns are concerned, correct?
Mhm.
Notice this one is in row 1 is this leading 1 is in a column that's to the right of the column that contains the leading entry of row 2, which is in a column that's to the right of the column that contains the leading entry of row 3. This is backwards for the requirement row echelon form. To be in row echelon form, the ones have to look like this. Do you agree? This is not row echelon form. This is. All right. All right. So any questions about what row echelon form is versus is not? Are we good on that? Ladies and gentlemen, if we went further, and got our matrix into what's called reduced row echelon form. What is the definition of a matrix to be in reduced row echelon form? Not just row echelon form, but reduced row echelon form. Well, we say a matrix is in reduced row echelon form if it is in row echelon form with the added condition that each row with a leading entry of 1 has zeros above the leading 1. In other words, for a matrix to be in reduced row echelon form, all right, simply put, you can only have 1s on the main diagonal of your matrix. 1s on the main diagonal or a 0. Well, first of all, the requirement is, first of all, each matrix has to be in row echelon form. But the second requirement is that off the main diagonal, ladies and gentlemen, you have to have nothing but zeros for your entries. All the entries that are not on the main diagonal have to be 0 in order for a matrix to be in reduced row echelon form. Oh, let's see here. This one doesn't have zeros here, does it? Let me see something. Is that correct? Let me see let me see the definition is here. Each row with a leading entry of 1 has zeros above the leading 1. Okay. Well, this is called, ladies and gentlemen, this is called reduced row echelon form because this last row does not have a leading 1. And because of that, we do not require that the entries above the leading 1 entry be 0. So these are not required to be 0 because this last row doesn't have a leading 1 entry. But if your row does have a leading 1 entry, all the entries above it have to be 0s. This is a leading 1 entry for row 3, all the entries above it have to be 0s. Leading 1 entry for row 2, all the entries above it have to be 0s. Okay? All right. Reduced row echelon form. All right, now the reason why I drag you through that, ladies and gentlemen, is now I'm going to show you as we inch closer and closer to actually being able to solve these systems using matrices. And so, ladies and gentlemen, I'm going to show you the criteria or the steps we go through for solving systems of equations using matrices. All right, step number 1. To solve a system of linear equations using matrices, this is step number 1. We need to have a 1 in the row 1, column 1 position of our matrix. In other words, our 1, 1 entry, ladies and gentlemen, has to be a 1. That's step number 1. Our 1, 1 entry of our matrix has to be a 1. If it's not a 1, we have to make it a 1. Specifically, we have to make it a 1 by using a valid elementary row operation. No, we can only use one of 3 valid elementary row operations to make our 1, 1 entry become a 1 if it's not already a 1. That would include maybe by interchanging any 2 rows of the matrix, I could force a 1 in the 1, 1 position. Or if that's not possible, maybe I could multiply. Maybe I could multiply row 1 by the reciprocal of the 1, 1 entry to force a 1 in the 1, 1 position. Okay, so either by multiplying row 1 by the reciprocal of the 1, 1 entry to force a 1 in the 1, 1 position, or interchanging any 2 rows of the matrix to force 1 in the 1, 1 position. Bottom line is I got to get 1 in the 1, 1 position. That's step number 1. Let me know when you have that copied down. Well, maybe I'll tell you what, we can maybe get both these steps in. Yeah, we can squeeze both steps in here. Step number 2 then. The next step is we need to use row 1 to make entries in column 1 below row 1 become zeros. They must all become zeros. And so, ladies and gentlemen, how do we do that? Well, in order to make all the other entries below the leading 1 in row 1, which is in the 1, 1 position, to become zeros, we're going to have to form new row 2s and row 3s by using row 1. Specifically, we're going to have to add a multiple of row 1 to row 2 to form a new row 2, whereby the 2, 1 entry would be a 0. Specifically, we're going to have to add to row 3 some constant times row 1 to ensure that the new 3, 1 entry is a 0. Okay. So when we make the 1, 1 entry a 1, all the other entries below that 1 have to become 0. We have to clear out the rest of column 1. I like to say we have to clear it out. Okay. When we do that, step number 3, wait a minute, do we have these steps accounted for? Steps 1 and 2? Everybody got them accounted for some way? Take a picture or,
I still have to take a picture of number 2.
okay.
Okay.
Everybody good on these steps so far? All right, then we move to step number 3. Now, ladies and gentlemen, the next step is that we have to make the row 2, column 2, or the 2-2 entry, we have to make that become a 1 next. We accomplish that by multiplying row 2 by the reciprocal of the 2-2 entry. Again, we must make the 2-2 entry become a 1. We accomplish that by multiplying row 2 by the reciprocal of the 2-2 entry. So in other words, ladies and gentlemen, we might have a number here, might have a number here. We got to make this 2-2 entry become a 1. This is called a 2-2 entry. We got to make this become a 1 next. Right? That's step number 3. And to make this 2-2 entry become a 1, if it's not already a 1, we have to multiply row 2 by the reciprocal of whatever this is. For instance, if this was a 2, we would have to multiply row 2 by 1/2. If this was a 3, we would have to multiply row 2 by 1/3. If this was a -5, we would have to multiply row 2 by -1/5 to force a 1 in the 2-2 position. Okay. All right. That's step 3. Step number 4. So once we get a 1 in the 2-2 position, ladies and gentlemen, we're going to then use row 2 to clear out the rest of column 2 below the leading 1, below the row of the leading 1 of the second row. So we got to clear out the rest of column 2. How are we going to accomplish that? Well, step number 4. Step 4 says we're then going to use row 2 to make entries in column 2 below row 2 become zeros. Specifically, if we have a 3x3, 3x4 augmented matrix, a system of 3 equations, 3 unknowns, we would have to take row 3 and add to it a multiple of row 1. Excuse me, we'd have to add a multiple of row 2 to row 3 to force the 3-2 entry to become a 0. Okay, that's clearing out the rest of column 2. So far, our matrix would look like this, where we'd have 1, maybe some number, we would have a 0, we'd have 1, some number, we'd have 0, and then we'd have 0, and then some number. So far, our matrix looks like this, ladies and gentlemen, after going through step 4. Steps 1 through 4, our matrix would look like this so far. You see that? You know what we're striving for? We're striving for row echelon form. That's why we're going through all these steps here. We're trying to get our matrix into row echelon form. Step number 5. Now we just have to make the row 3, column 3 entry, or the 3-3 entry, become a 1 by multiplying row 3 by the reciprocal of the 3-3 entry. When we do that, ladies and gentlemen, our matrix now will look like this. 1, these will be some numbers. This will be a 0. This will be 1. This will be some number. This will be 0, 0, and 1. Then our matrix will look something like this, where we got 1s on the main diagonal. Notice that. By the time we get through step 5, our matrix is going to look like this. Okay? Then, ladies and gentlemen, we're essentially almost done. All we have to do then is use what's called back substitution to recover our coordinates of our ordered pair or ordered triple solution to our system. And we got it. Okay? So it's those 6 main steps that are going to enable us to solve systems of equations using matrices. And now I think it's time, ladies and gentlemen, just to dive in and start showing you examples to basically employ these 6 steps here. Or if it's a smaller system of 2 equations, 2 unknowns, we don't have to use all these steps. We just have to use 4 steps. Okay. All right. So let's just let me demonstrate several. All right. Solving a system of equations by using matrices where we get our matrix into row echelon form, ladies and gentlemen, is called Gaussian elimination. So we're going to solve by Gaussian elimination. In honor of Carl Gauss, who was a prominent mathematician. You get a chance, you can look at Carl Gauss's biography later on. He made tremendous contributions to the field of mathematics. Okay. All right, here we go. We're going to try to solve the system of two linear equations and two unknowns. There's a picture of Carl Gauss on the wall in the Math Empowerment Center or Math Enrichment Center, the tutorial lab that I hang out in on Mondays and Wednesdays. We're going to try to solve this harmless little system of two linear equations and two unknowns by using Gaussian elimination. And when I say Gaussian elimination, that means we're going to be using matrices to solve this system. So how do we do it? Well, first of all, we got to write our system in the form of a matrix. What size matrix is this going to be? How many rows by how many columns?
2 by 3.
It's going to be a 2 by 3 augmented matrix. Here we go. 2, 3, vertical line, negative 13. Second equation, 1, 4, vertical line, negative 14. There's our system in the form of a 2 by 3 augmented matrix. Now we're going to solve this system utilizing our elementary row operations and striving to get this matrix into what is called row echelon form. Okay, we got to get this matrix into row echelon form. What was the first step, ladies and gentlemen? What was that first step? What was that first step? We need to make the 1, 1 entry become a what? A 1. How, ladies and gentlemen, do I make this 1, 1 entry become a 1? Because right now it's not a 1. What valid elementary row operation can I subject this matrix to force a 1 in the 1, 1 position?
Divide the first row by 2.
Okay, actually, we would not divide. Technically, we would
Right.
multiply the first row by 1/2. Do you agree? That would be one thing we could do, 1/2. Isn't there an easier way, though? We could do that. We could do that, though. That would work. But isn't there an easier way? What other valid elementary row operation, instead of multiplying row 1 by 1/2, which we could do, it would work, could we utilize to force a 1 in a 1, 1 position, an easier way?
We could multiply row 2 by -1 and then add them together.
We could do that too, but that's even more difficult than the first thing you said. No, what is the easiest way to force a 1 in the 1, 1 position? There's one more elementary row operation. You cited 2 of them. There's one more. What can we always do at any time in a matrix?
Flip the rows.
Flip the rows. Ladies and gentlemen, let's do that. So therefore, let's just interchange rows 1 and 2. That's the easiest way. Those other ways would have worked, by the way. Just interchange the 2 rows. Perfectly legal move here. That's a valid elementary row operation. Wait a minute here. This isn't right. This should be -13. That should be -14 up there. Hold on a second. We just interchanged the rows. Do you agree? That's all we're doing here. Perfectly legal. Gotta let that dry. All right. Now, ladies and gentlemen, what's the next move? We have a 1 in the 1, 1 position. That's great. What do we do next? Well, now we're going to use row 1 to clear out the rest of what? Column 1. We have to make all the entries below row 1 become 0 in column 1. We got to make these entries become 0. How do we do that? To do that, we're going to have to add a multiple of row 1 to like row 2 to form a new row 2, where the 2, 1 entry has to become a 0 though. All right. So, ladies and gentlemen, how do I force a 0 in this position here using a valid elementary row operation? What multiple of row 1 could I add to row 2 to make this entry become a 0?
-2.
-2 times what? Row 1, correct?
Yes.
All right, so here's what we're going to do. Do our correct. Let's see where to write this here. So what I'm going to do is I'm going to take row 1 and I'm going to multiply it by what? -2. And to that, ladies and gentlemen, I'm going to add row 2 to form a new what? Row 2. Does that make sense? I'm going to take -2 times row 1, add it to row 2 to form a new row 2, where this entry has to become what? 0. That's why I'm multiplying row 1 by -2, because I know, what do I have to add to 2 to make 2 go to 0? -2, right? Where am I going to get the -2 from? I'm going to multiply row 1 by -2 and then add it to row 2. Okay. So when we multiply row 1 by -2, what row do we get? When I multiply row 1 by -2, what row do I get? -2 times 1 is -2. -2 times 4 is -8. -2 times -14 is what? 28. We're now going to add this to row 2, which is 2, 3, -13. What new row 2 am I going to get now? 0. We add these together now. 0. What does this give you? -5. And this gives you what? 15. So therefore, ladies and gentlemen, my equivalent matrix now becomes this: 1, 4, -14. Row 2 has undergone a facelift. It's now 0, -5, 15. Everybody with me? We got our matrix down to this now. We're striving to get this into row echelon form. Why is this not row echelon form yet? Why is this not row echelon form?
The -5.
Because the first non-zero entry you have to run into from left to right in any row has to be what? A 1. We have to make this become a 1. And so, ladies and gentlemen, we're down to step number what? Step number 3. That says we need to make the 2-1 and the 2-2 entry, excuse me, we need to make the 2-2 entry become a 1. To do that, we multiply row 2 by the reciprocal of the 2-2 entry. What's the reciprocal of -5?
-1/5.
-1/5. So here's what we're going to do. We're going to multiply, ladies and gentlemen, row 2 by -1/5 to form a new row 2. That's a valid elementary row operation. You can always take any row and multiply it by a non-zero constant to form a new equivalent row. So here we go. Notice row 1 does not change. We're only going to change row 2 again. So I take -1/5 times the entries of row 2. What's -1/5 times 0? -1/5 times 0 is 0. That keeps the 2-1 entry as a 0. -1/5 times -5 now forces the 2-2 entry to become what we wanted, a 1. What's -1/5 times 15 over here? See, what I'm doing is I'm taking -1/5 times row 2 to form a new row 2, which is going to be 0, 1, -3, correct? -3. Now my matrix is in row echelon form. Ladies and gentlemen, this matrix we say is in row echelon form. And since it's in row echelon form, we can now use back substitution to find the X and Y coordinates of the ordered pair solution to this system. Remember, the first row column gives me pertains to the coefficients of the X variable. The second column pertains to the coefficients of the Y variable. The right-hand side column is the constants. So from this second row, what equation do I have from the second row? What equation do I have from the second row? I have 0x plus 1y equals what? -3. So what equation do I have? Second row.
Y equals -3.
Y equals -3. There's your Y coordinate of your ordered pair solution. To get the X coordinate, we're going to use row 1 of this row echelon form matrix and write the equation. This first row indicates we have the equation 1x plus 4y equals what? -14. Now we back substitute. We take the -3, back substitute it up into the first equation for y, and then we can solve for x. It's called back substituting. This is called back substituting. And therefore, our equation one, after back substituting -3 in for y, our equation one is going to become what? X plus 4 times -3 is equal to 14. X minus 12 equals -14. -14, add 12 to both sides, and X is equal to -2. And we're done. We have the X and Y coordinates of our ordered pair solution, -2 and -3. So -2, -3. We have just solved this system, ladies and gentlemen, utilizing what's called Gaussian elimination, which makes use of matrices and elementary row operations to get your matrix into row echelon form. Any questions with what just happened here? First, we interchanged rows 1 and 2. Then we used row 1 to knock out this 2-1 entry to make it a 0. We accomplished that by adding to row 2, -2 times row 1. We got this new row 2. And then we got the 2-2 entry to become a 1 by multiplying row 2 by -1/5. Okay. All right, let's take a look at another one here. All right, so this system with 2 equations, 2 unknowns here. All right, let's see if we can apply this to a system with 3 equations and 3 unknowns. Again, please do take the time outside of class to look at some of the examples in this section. I think your author does a marvelous job in, showing all the steps and everything. It's only going to help solidify this all in your mind, ladies and gentlemen. First of all, we're going to rewrite this system in the form of a what size matrix?
3x4.
3x4 matrix. Now, if you took this problem and presented it to a computer system, you would enter this system in the form of what's called a 2x3 array. They're called arrays in computer science, not matrices, but arrays. Arrays are the same thing as matrices, though. 2x3 array. Then you'd have the computer work on it and solve it. The computer could solve the system within 1/1,000,000th of 1 second. Done. Whole thing. I'll show you on your calculator how you can solve these systems to check your answers, ladies and gentlemen. After we get done drudging ourselves through the mud on this one, I'll show you how fast your calculator can solve this system. All right, ladies and gentlemen, we want to solve the system of 3 equations and 3 unknowns. Our job is to get this matrix eventually into row echelon form. And then by back substituting, we'll be able to recover the X, Y, and Z coordinates of the ordered triple solution to this system. First, I got to make the 1-1 entry become a 1. What's the easiest way to do that? How can I make the 1-1 entry become a 1? Easiest way.
Move the middle row to the top.
So we'll interchange what 2 rows?
Row 2 and row 1.
Rows 1 and 2. Just interchange rows 1 and 2. That'll force a 1 in a 1-1 position. Piece of cake. Row 1 becomes row 2. Row 2 becomes row 1. Just interchange the rows. Our new equivalent matrix is now this. That's equivalent to as if I just flipped the first equation and made it the second equation, made the second equation the first equation. It's still the same system. Makes sense why it would still be the same system. You're just interchanging the equations. It doesn't change the solution to the system. I think I did this again. That should be 37 there. So maybe I'm just a little too excited here. That should be 37. All right, notice we did not do anything to row 3, not this time. All right. I'm gonna let that dry and I'll put 37 in there. Ladies and gentlemen, what's the next step now? Well, the next step is we have to somehow, some way use row one to knock out all these entries below the first row. We got to make all these entries in column one here and here become zeros. We got to make this 2-1 entry become a 0 and the 3-1 entry to become a 0 by using row one to accomplish that. So we're going to have to add a multiple of row one to row two to make this 0. We're going to have to add a multiple of row one to row three to make this entry become a 0. So what would be those things we need to do? Well, to make this 2-1 entry become a 0, we're going to have to take row one and multiply it by what? What am I going to have to multiply this by and then add it to this to make this 0? What do you add to 3 to make it 0?
-3.
Where am I going to get the -3 from?
Multiply row one by -3.
So what I'm going to do is I'm going to take row two, and to it, I'm going to add -3 times row one. That's going to form a new row two. So I'm going to pencil back in row one. Row one does not change here. By the way, this is 37 now. Row two is about to undergo a facelift, ladies and gentlemen. I'm going to take -3 times row one. You can speed this up just by putting a little -3 here. Now, what's -3 times one? What's -3 times one?
-3,
And what's -3 plus 3?
0,
0. What's -3 times 3? -3 times 3.
9,
-9. What's -9 plus 7?
-2,
What's -3 times 10?
-30,
-30 plus 22.
-2.
-30 plus 22.
Oh my gosh. 8.
-8? I think you joined my club.
I did.
What's -3 times 37? Calculator might help, ladies and gentlemen. -3 times 37.
-111.
Add that to 83. What does the new 2-4 entry become? -3 times 37 is -111. What's -111 plus 83?
-28.
-28 is the new 2-4 entry. Done. Now we're going to make this 3-1 entry become a 0 by multiplying row one by what? What do you add to -2 to make it 0? 2? Where are you going to get the 2 from? We're going to multiply row one now by 2 and add it to row what? 3. So we're going to take row 3 and add to it 2 times row 1 to form a new row 3. See this here? We're going to take row 3, add to it 2 times row 1 to form a new row 3. Now you can change this little -3 to a little 2. What's 2 times 1?
2.
2.
What's 2 plus a -2?
0.
The new 3-1 entry becomes a 0. That's a requirement. What's 2 times 3? 2 times
6.
3, 6. What's 6 plus a -5?
1.
The 3-2 entry becomes a 1. 2 times 3 is 6. 6 plus -5 makes this a 1. What's 2 times 10?
20.
20.
20. 20 plus -18. What's
2.
2 times 10? 20 plus -18 is 2. The new 3-3 entry becomes a 2. What's 2 times 37?
78. Or wait, no, not 78.
74.
Welcome to my club. 2 times 37.
74.
74 plus a -66.
8.
Good. 8. Do we understand how we got our matrix down to here so far? Everybody, are we following this? We're getting closer to row echelon form. Why is this not in row echelon form yet?
The second row doesn't have a 1, and the 1 in the third row is too far forward.
Exactly. It's not row echelon form. Because the first non-zero entry you have to run into from left to right in any row is a 1. We run into a -2 here. So the next move, ladies and gentlemen, now is to make the 2-2 entry become a 1. How do I legally, using a valid elementary row operation, make this become a 1? Some of you are saying, let's just interchange rows what? 2 and 3. Could we do that? You know, ladies and gentlemen, that would be a valid move. If you interchanged rows 2 and 3, would I not force a 1 in the 2-2 position? And still keep these entries 0? You know, you could do that. Another way you could force a 1 in the 2-2 position is to multiply row 2 by the reciprocal of -2. That's to say we could multiply row 2 by -1/2. That would force a 1 in here. So which way you want to go? Doesn't matter to me. You want to interchange rows 2 and 3?
Yes.
You could certainly do that. Perfectly legal. All right, so what would be our equivalent matrix after taking care of this elementary row operation? All right, so row 3 is going to become row 2. Row 2 is going to become row 3. Perfectly a legit move. Notice we're getting closer to row echelon form. We got 1s on the main diagonal here, but we have to do what? What does this entry have to become though?
0.
It has to become a 0. How are we going to make this entry become a 0? Well, we're going to use row 2 now to make this become 0. Specifically, we're going to have to add a multiple of row 2 to row 3 to make this entry become a 0. What do you add to -2 to make it 0? 2? Where are we going to get the 2 from? We're going to multiply row 2 by 2 and then add it to row 3 to form a new row 3. So what was that again? We're going to take row 3 and add to it 2 times row 1 to form a new row 3. That's what we're going to do. We're going to take row 3, add to it 2 times row 1, and then that will form a new row 3. Notice we're not changing rows 1 and 2 here. Pencil them back in. All right. I'm going to put a little, wait a minute. This should be times, not row 1, but row what? 2 times row.
3.
No, that should be times row 2. My bad. So then what we're going to do is we're going to add to row 3 2 times row 2. I'm sorry, row 3. We're going to add to it 2 times row 2 to form a new row 3. Okay, put a little 2 here. What's 2 times 0?
0.
2 times 0 is 0, and 0 plus 0 keeps this entry as a what? 0?
0.
What's 2 times 1?
2.
2 plus -2 makes this entry become a what now?
0.
0. What's 2 times 2?
4.
4. 4 plus a -8. Turn this
-4.
into, yeah, you're right, -4. 2 times 8.
16.
16 plus a -28. -12. 2 times 8 is 16. 16 plus -28 is -12.
You're right. Yeah.
You guys
Yeah.
don't trust me. I don't blame you. I think it's I think I think it's a -12. I've already demonstrated my incompetence today. 2 times 8 is 16 plus a -28 is -12. You're correct. All right, here we go. All right, how do I redeem myself? Now, ladies and gentlemen, do you agree this is pretty close to row echelon form? I just have to make this entry become a what? What are we going to make this entry become?
A 1.
A 1. And how do we do that? Well, we cannot interchange any 2 rows here. That's not going to help. So there's only one other choice. I have to multiply row 3 by the reciprocal of -1/4. I'm sorry, by the reciprocal of -4, which is what? -1/4. I am so not having a good day. So ladies and gentlemen, I'm going to form a new row 3 by multiplying my existing row 3 by -1/4. Do you agree? And we're going to form a new row 3 by doing that. You can always multiply a row by a non-zero constant. That's a legal elementary row operation. When we do that, our matrix will become this equivalent matrix here. All right, here we go. I'm gonna put a little -1/4 out here. What's -1/4 times 0?
0,
This entry remains as a 0. What's -1/4 times 0?
0,
0. -1/4 times its reciprocal, -4.
1,
1. -1/4 times -12 is -12,
Three.
-12 over -4, which is +3. Ladies and gentlemen, what form is this matrix finally in?
I
What do we
can't
call-
say.
Oh, okay, it's row. What is that called? Row echelon form. Row echelon form. Now we're in business. To solve for the XYZ coordinates of our ordered triple solution, we just use back substitution. From this third row, I should generate what equation? Remember, this is your X column, your Y column coefficients, your Z column coefficients, and your right-hand side constants. So, ladies and gentlemen, from the third row, what equation do I generate from the third row?
Z equals 3,
Z, 1Z equals 3. That's your Z coordinate. The second row generates what equation? 0x plus 1y plus 2z equals 8. So we just say y plus 2z equals 8. Y plus 2z equals 8. First row generates what equation?
x plus 3y plus 10z equals 37.
That's it. X plus 3y plus 10z equals 37. We know z is 3. We back substitute it up into the second equation for the z variable and then solve for y. Therefore, this implies upon making that substitution, we have y plus 2 times 3 equals 8, which implies y plus 16, y plus 6 equals 8, which implies that y is equal to 2. We got our y coordinate now. Now we know y and z. We back substitute these values up into our first equation. 2 comes up here and drops in for y. 3 comes up here and drops in for z, for z. And then we can solve for x, agree? Called back substituting. So, ladies and gentlemen, making these substitutions in equation 1 becomes then x plus 3 times y, but what's y? 2
Yeah.
plus 10 times z, what's z? 3 equals 37. Do you agree with solve for x now?
Mm-hmm.
Or we hopefully will. So x plus 36 is equal to 37. Subtract 36 from both sides. We get x is equal to what? 1. We are finally done. Ordered triple solution is 1, 2, 3. See how we solve this, ladies and gentlemen? This is called the what procedure using matrices. What's the name of this procedure in honor of that mathematician? What's it called?
Gaussian's elimination.
Yeah, you're right. You're right. Gaussian elimination or Gaussian elimination. You are correct. Gaussian elimination. That's quite a procedure, isn't it, ladies and gentlemen? It's quite a procedure. You think you might have success on one like this? Gaussian elimination. Elementary row operations to get your matrix down into row echelon form. And once you have it down to row echelon form, then by back substituting, you can recover the coordinates of the solution. By back substituting, then, ladies and gentlemen, you can recover the coordinates of the solution. Do you agree? It's called Gaussian elimination. All righty. Now, I know we have those fancy graphing calculators out there, ladies and gentlemen, and I'm going to show you how to solve this system using your graphing calculator so that you can at least use your calculator to check your answers on maybe an exam or a quiz. So let's go get our graphing calculator. We're going to enter this system in the form of a 3x4 matrix, and we're going to show you how the computer can solve this a little bit quicker than we solved it. Okay. Let's go grab the computer. I don't mind if you use your calculator to check your answer. In fact, I encourage you to do so. All right, turn your calculator on, ladies and gentlemen, and we're going to show you now how to first of all enter this system into the form of a matrix. So the first thing we have to do is we have to cast this linear system into the form of a matrix. How do we do that? Well, first we have to go into our matrix mode. Above your reciprocal key, right below your math button in blue is the word matrix. So I'm going to have to hit my second key followed by the reciprocal button to dive into the matrix mode. Is everybody there in the matrix mode? Let me know when you get there. All right, once in the matrix mode, we're going to select edit because we have to enter this system into memory. So with your cursor sitting on matrix name A, let's go over to edit. I'm sorry, we got to go over to edit. Hit your right arrow key, navigate to edit. With your cursor sitting on matrix name A, hit enter. We now need to enter in the number of rows by number of columns. This is a system of 3 linear equations of 3 unknowns. It will be a 3x4 augmented matrix. Type in 3, hit your right arrow key, type in 4, hit your enter button. It's now a 3x4 augmented matrix. We just have to enter in our system. And the last problem we just solved, the first row was 3, enter, 7, enter, 22, enter, and then 83. The second row was 1, enter, 3, enter, 10, enter, 37, enter. The third row was -2, enter, -5, enter, -18, enter, -66, enter. We now entered this system in the form of a 3x4 augmented matrix into our calculator. Did we all accomplish that? I'm assuming, ladies and gentlemen, unless you speak up, that we're cruising along out there. Gotta let me know if you're hung up on something. We doing okay? Anybody having a hard time entering the system into their calculator? 3x4 augmented matrix. All right, we're done with that. I'm assuming that we got it entered in. So let's now, ladies and gentlemen, let's do what next? Let's get out of this by hitting second mode to quit. That system has not been erased. It's still in memory in the calculator. Let's go back to matrix now. Second reciprocal button. But this time we go over to math. Matrix math. Scroll down. Keep scrolling down, you run into this very powerful little function called the RREF function. That stands for Reduced Row Echelon Form. Reduced Row Echelon Form, RREF. Do we all see that function? Hit enter to activate the function. We now need to type in the name of the matrix that contains our system. Uh-oh, do we remember the name we put it in? What matrix name did I put my system in? Do you remember? It was matrix what? I think it was matrix A, wasn't it? We got to go back to matrix mode now. Second reciprocal button, stay on names this time. Notice matrix A is the one I put it into because I can see the dimensions of the matrix 3x4. Hit enter. Close parenthesis. You ready for this? Hit enter. Boom, done. System has been solved, ladies and gentlemen. The first row generates the x coordinate. 1x equals 1. The second row, 1y equals 2. The third row, z equals 3. Solution is 1, 2, 3. Everybody see how that worked? The RREF function, the reduced row echelon form. We say that this matrix, ladies and gentlemen, is not only in row echelon form, they've actually gone farther. Your calculator's taken it further. It's taken it all the way down to what's called reduced row echelon form. Because notice above the leading ones in each row, you have zeros. That's called reduced row echelon form. Or that's to say you have ones on the main diagonal and zeros offset the main diagonal. Off the main diagonal are zeros. When your calculator's in reduced row echelon form, your solution just lies in the lastmost column, your X, Y, and Z coordinates there. Okay, we're done with that. All right. So that's that. All right, well, ladies and gentlemen, I mean, can you think you might be able to solve a system on your own now? What classwork are we up to by now?
4, I believe.
I believe it is 4. It's gotta be at least 4, right? I think. All right, try this one here. This will be the last classwork today. We're almost out of time. Okay. Solve by Gaussian elimination. And here's the system: 2x minus 8y plus 54z equals -4. Please use your calculator for elementary operations to speed this up. You don't have to go back to basic math, ladies and gentlemen. You know, you can use the calculator to take care of your additions, subtractions, multiplications, and divisions. But I do want you to try to demonstrate the elementary row operations you're utilizing to get this matrix into row echelon form, so that through back substitution, we can recover the order triple solution. So see if you can solve this system, okay? All right, go ahead, go to it. Oh, when you use an elementary row operations to try to get your matrix in the row echelon form, there may be times when you have fractions that surface. Please don't turn them into decimals. You think fractions are messy, you ought to see how messy decimals are. Don't ever turn them into decimals, leave them as fractions. You can reduce the fractions, but leave them as fractions. All right, I got the order triple solution, -1, 7, 1. Anybody survive to the end?
Yeah, I got that too.
I'll be darned. All right, as you can see, ladies and gentlemen, these are just gonna require a little bit of practice here, to say the least. They are tedious problems. Please look over some of those examples in section 6.1. Follow what your author is doing in those examples, ladies and gentlemen. Study those examples in detail. I think it's only gonna help your cause, okay, as to what's going on here. All right? So again, I know I sound like a broken record, but please spend some time and look at the examples in section 6.1 and follow what your author is doing. All right. I think it's going to complement with what it is I was trying to convey here today. All right, you guys have a great weekend, and I'll update the homework on Alex. And there is no assessment this week. Oh, the chapter 5 quiz is still going. Do you agree? That chapter 5 quiz is still going.
Yes, it is.
It's due tomorrow, right?
I believe it's the 18th.
I believe it
Yes.
was midnight, the 18th. Yeah. Mhm,
I actually had a question about the quiz.
mhm.
Sunday I